My name is Adrian Fanjoy. I'm the Technical Director for Computer-Aided Technology. We are a VAR, reseller of SOLIDWORKS in the Midwest. We're based out of a suburb of Chicago called Buffalo Grove. Josh Altergott is our Tech Support Manager, and we work together on a lot of presentations, and more specifically on anything that involves performance of SOLIDWORKS. It's kind of a passion of ours we've developed over the last, I believe it's been 6 years since we started doing this form of testing that we're going to show to you guys today.
It's more of an obsession, by the way, than a passion.
An obsession, a passion, a lust, however you want to phrase it. And what we'd like to do is make sure everyone understands the ground rules as we go through this presentation. Last year we had one presentation for 90 minutes that covered hardware and configuration of that hardware, as well as modeling methodology. This year we broke it out into two one-hour sessions. The hardware session is today. The modeling methodology session is Wednesday at what time? Afternoon.
Yeah.
I know that. So look for it if you're interested in modeling methodologies as well as hardware. Now, the reason we lengthen it out is we have a lot of material that we have to go through. We always were pushing up against a rock with 90 minutes. We figured this was a good way to broaden it out a little bit and to allow you guys to ask more questions. Okay? So what we're going to do is we're going to open the floor for questions throughout the presentation. Just raise your hand, let us know you have a question, blurt it out, whatever you want to do. We will answer the ones that we can as we go. We may end up pushing some to the end if we don't think we have the time to answer it, or if we start running out of time as we go through the presentation. This is the first time we've done this presentation like this, so the timing is still a little bit obscure to us. So, you ready?
Ready. So the objective of this presentation, what we want to do is better understand the benefits of different hardware investments, learn how to apply performance data to purchasing decisions. As we all know, when we're looking to get new machines, trying to talk to our engineering manager or our IT group, they're always looking for justification as to why we need that hardware. The data that we collect here, that's what we're hoping that you guys can take to them to use that for your purchasing decisions. And the biggest thing that we're trying to do is make the workstation faster than the user ultimately.
So how we're going to handle this today, this is pretty much the agenda. Introductions. You know us now, right? Josh, I'm Adrian. I'm good looking. He's Josh. All right.
I got to stand on the stage.
Like we said, we've been doing this for 6 years. So one of the things we're going to do is we can't test everything every year and bring you guys the results. We're going to go through some of the results from previous years, things we've learned that are just givens at this point, just to make sure everyone's on the same page and understands where we're kind of coming from. Then we're going to talk about our new benchmarking method. We've changed it a little bit since we've done it in the past. Has anyone seen this presentation in the past? We got a few. Wonderful. Wonderful. Okay? So we've made some adjustments that are going to help us be a lot more dynamic and a lot more versatile and appeal to a much larger audience. Then we're going to go through the hardware comparisons that we came up with this benchmark this time. We focused mostly on RAM and CPU speed this time. Then we're going to go into graphics. We're going to spend quite a bit of time on graphics and the different testing that we did there. It was somewhat enlightening. I hope you guys get a lot out of it. Then we'll sum it all up and keep the floor open for questions till they kick us out. All right?
All right, so results from previous adventures. Like Adrian said, we've done this for a long time, and we got a lot of different data. Some of this is stuff that's known to us at this point in time, but we want to make sure you guys are all aware of it as well. Really? You're going to start that? All right. So where we're going to start off talking today is talk about solid-state hard drives. Solid-state hard drives are now the standard for operational tasks at this point in time. And we still need large volume storage. Any type of data that you're storing, archiving, that can be, is still best served with spinning drives. They're cheap, they're efficient, they get the job done. From our testing, what we've seen over the years, switching from a 7,200 RPM hard drive to an Intel SSD improves performance by as much as 15%. You can see on the chart there, kind of what we've experienced, 7,200 RPM all the way up SSD, and even into a Revo card. Right now, best bang for your buck is a solid-state hard drive, though.
Now, we also in the past have tested antivirus software across the network. And if you're storing your files on the network, a lot of customers run into that problem of, is the antivirus software impeding my SOLIDWORKS performance? It's a big question. Anyone here in IT instead of engineering? Good, we'll talk about them. Okay. The IT guys will tell you time and time again that the antivirus software does not impact your performance, has nothing to do with it, and the results are up too soon.
That's why you built the slides, man.
It is the way I built the slides. It is my fault. But basically what it is we ran it with the antivirus software scanning on both the server and the client because that's the one that unnerves me the most, right? And remember, we're going across the network here, so we've got that overhead as well. The benchmark we ran for 6 hours and 52 minutes. That's not trivial, right? It's almost a day's worth of work. It's definitely a day's worth of Josh's work. He's always cutting down an hour early. Then we turned off the scanning for the client. And we only got a little bit of benefit, okay? But when we turned off the antivirus scanning for both the client and the server, now we've got a noticeable difference. 15% is nothing to sneeze at. If you guys could get 15% more out of your day, you'd be happy about that, right? So there's a lot to be said for making exceptions in your antivirus software to exclude SOLIDWORKS files, okay? Now, this IT people really hate for me to say, but one thing we know of, it's like Apple. Anybody use an Apple here, a Mac? One of the things they always tell us is Macs are great, they never get viruses. That's because no one uses a Mac, so no one writes a virus for a Mac. No one writes viruses for SOLIDWORKS files. It doesn't happen. Now, some hacker's going to hear my presentation one day and do it just for a lark, I'm sure. But we can kind of count on a little bit of security just in that. If we scan everything coming into the building and not scan for SOLIDWORKS files going across our internal organization, we're probably still safe and we get the 15%. But what would be better? Not going across the network at all. Because look at what happens to the benchmark when you run it off the local SSD. What happened?
Kind of just went blank for a minute there.
What's next?
There we go.
Are you messing with me?
I'm not messing with you. You can ask the guys out here. I did not touch anything.
Now I'm all nervous. Okay, but if we're running local to our machine on the local SSD, we drop 68% improvement. That's a huge deal. You know what? This screams loud to the loud to the world. Use a PDM system. Use a system that will allow you to store, archive, rev control, all on the network, gives you all the backup and all the security you need, but when you're working on the files, you're working locally. And that's going to save you a boatload of time. Yes, sir?
So the 60% is compared to the opening over the network with the antivirus full on server A.
Exactly. Antivirus full on both sides and going over to the network. That's our baseline. Good point. Good point. Thank you, Wes. What the question was is he's asking what was the baseline? What are we comparing to? And this is local, on the local hard drives operating SOLIDWORKS versus the files being stored on the network with virus scanning on both sides. Big improvement. I'm scared to hit the button again.
I know. All right. So the next thing we want to talk about is multi-core. SOLIDWORKS, as I hope most people know at this point in time, uses 2 cores, and we're talking just for SOLIDWORKS. The OS can use an additional 2 cores. Other applications are going to add to that load. Simulation and rendering, they take advantage of many cores. We'll talk about those in a couple of slides. So what we found here, 2 core was our baseline, and you kind of have about 2-hour runtime. You drop that thing down to 1 core. Now SOLIDWORKS and the OS all have to fight for that 1 core. It's almost 300% slower at that point in time.
Aren't you glad you can't buy 1 core? Because you know your IT department tried to do it.
They would. And now, as we move up, 3 cores, we gain, another 13.8%. 4 cores, we're gaining a little bit more. 6 cores, we're only gaining 0.4% over that 4-core processor at that point in time. So, you can kind of see where we're at that point. So, where multi-core is more. Simulation or simultaneous applications such as Outlook, your ERP, and purchasing systems. Simulation, photo rendering. Those are the other 2 places where we take advantage of the multi-core processors.
So, with simulation, the 2 different types of simulation that we dealt with here, they were both SOLIDWORKS simulation. We didn't go into Abacus and ANSYS and all those things that take advantage of this stuff much more effectively than we do. But going from 4 to 6 cores, you get a jump of 17% on a FlowWorks simulation. The FlowWorks simulations that we did, okay? There's a lot of options out there. There's a lot of different things you can do. Some will give you more of a performance hit. Some will give you less. Going from 4 to 8 gave us 20%, and 4 to 16 cores give you 29%. What you got to decide is what your ROI is and how you're going to be using the machines, okay? Are you trying to run simulations in the background while you're operating SolidWorks? Are you going to be running your ERP system and Outlook and everything else at the same time? How are you going to load this machine up, and how much power do you need? And in static simulation, not as great an impact there. Flow has been much more optimized for multi-core than the static simulation has. And it's important to note here too, because it affects the next slide a little bit, hyper-threading is off. We had no benefit in turning hyper-threading on for simulation, okay?
So when we look at photo rendering with a multi-core processor, going from 4 to 6 cores jumps us up 17%, 4 to 8 cores we're 51%, 4 to 16, we're now 74% faster. For those of you who have done photo rendering, how many people do photo rendering on a regular basis? A few people. Yep. What you see, when you see all those little dots on the screen as you're rendering inside SolidWorks, that's all the cores that are being used. So we throw hyper-threading in as well. That's as much as 16% faster. And you can see in the performance curves there what we get as we go from 4 all the way up to 16 gig of RAM and the hyper-threading on and off. We definitely get some added benefit with all of that.
And for photo rendering, just so everyone knows, we haven't found a limit to the improvement in speed yet. The most that we've been able to test is 16 cores, and it keeps getting faster and faster every time. I don't know what happens at this point because we haven't tested it. When we expand and go to multiple machines, farms, and run 32 cores, 64 cores. We'll have to see what happens as we do that and further test when I decide I want to spend that kind of money on cores. Yes, sir.
Obviously, the number of cores is not linear to the speed increase, but is the clock speed linear, or have you done that kind of study?
We have not done clock speed test with simulation. Sorry about that, but we haven't done it yet. Now, other things we've tested in the past that we're quite fond of. We tested RAID arrays, RAID 0 and RAID 1, mirroring and some other aspects of it so that we could determine if writing and reading from 2 disks simultaneously helped SolidWorks in its performance. It had little or no effect in our test, okay? Little or no effect. Not a lot of people trying it anymore, so we don't test it anymore. Optimizing the OS visual settings, some stuff in Microsoft Windows to turn off some of the overhead. Now that we've moved from the 32-bit world into the 64-bit world and we get all that RAM that comes along with that, faster, it doesn't make a bit of difference anymore. Nothing that we can tell you to turn it off. It's just not worth the effort. Turning off the arrow theme can cause damage to some of the things that SOLIDWORKS needs to operate. The problem that I'm having is figuring out how you turn off arrow, because there's a whole list of things that they've told me if you turn these off, arrow's gone. Well, what if I turn off all but one of them? Or how about if I turn off half? I don't know when arrow is gone and when it's not, because there's like 12 switches. There's not one. Actually, there's closer to a couple dozen, but still. It is important to know that it is recommended not to turn off Aero, though. Using swap for RAM, just buy more RAM. I don't want to deal with swap anymore, and we shouldn't have to. So if you're doing this, if you're actually swapping and you've bought 16, 32 gig of RAM, and you're still having problems, and you need to come to the modeling methodologies presentation, because we got to work on that next.
Exactly.
Is that for simulation or is that for graphics?
I'm sorry, what is for that?
Back to the memory and the swap, that's for simulation, right?
It's for SolidWorks modeling. Yeah, SolidWorks modeling takes a huge hit if you start using swap space. But we've pretty much stopped using swap space when we started using 8 and 16 gig of RAM on a single machine. That eliminated that for the most part. So thus, we don't test it that much anymore. Add-ins. Add-ins are a hard thing to isolate because everyone has a different need there, right? In that, some people have FlowWorks running in the background. Some people have photo rendering. You don't know. And it depends on whether you're using it or not, how much it pulls. So the real lesson with add-ins that you need to take away is don't turn them on if you're not going to use them. Because they are going to take a little bit of your RAM. They are going to take a little bit of your processing just to be on. And then, well, more importantly, someone else wants to use it. And you got it and you're not using it. So that's a bad thing in general. And then optimizing SolidWorks options, we do get up to a 16% increase in performance in SolidWorks modeling if we optimize per Josh's instructions, and we'll go through those on Wednesday because that's modeling methodologies. But it's an important thing that we do test.
Exactly. So the benchmark. The benchmark that we run for all of our testing is what we want to talk about here. Now, where we start is with the hardware side of things. Box Technology, we partner up with them for several years. They're a great partner. They loaned us this year an Apex 2. This is kind of their standard for SolidWorks at this point in time. Comes with an i7, 4-core. We have 4 gigahertz overclocked to 4.5. 4 is their standard. You can add in the overclocking. We threw in up to 32 gig of RAM. 16, I think, is the standard for the most part. Yeah. Right, Shoaib? Okay. And it's dual channel DDR3 RAM, solid state hard drive, it's 180 gigabyte. And we went with a mid-range NVIDIA Quadro card. So this is our baseline or our test machine that we worked with this year. And now the previous version of the benchmark. Like Adrian said, we made some changes to the benchmark. Our older version of the benchmark simulates many aspects of SolidWorks use. Took almost a day's worth of runtime. We were locked into testing with graphics manipulation turned on, and it only worked with one model. We had one giant assembly, and that's the only thing that it would work with. So we wanted to change that up a little bit, and that's where we come in with the new benchmark.
So by graphics manipulation, what Josh meant is spinning and rotating and zooming and panning the model. What we wanted to do is test SolidWorks without that and test graphics separately. So we rebuilt the benchmark to give us a choice to turn off and on the graphics manipulation portion. Helps us run the benchmark with just SolidWorks calculative modeling effort to give more of an apples to apples test. At least we're more comfortable with it now. It's but right now it works with any SolidWorks model, virtually any SolidWorks model, meaning we haven't found something we've tried to test that wouldn't work. We can go with small assemblies, very, very large assemblies, but they all work in the benchmark. But this is around alpha mode right now, alpha beta in this particular program, so it doesn't simulate as much as our last one did. We're doing fewer operations in SolidWorks, but we're building it as we go. And so, thus, it's a shorter runtime on this one. But the key here is we're able to test any model. It's beautiful. Any model, any environment, any place, we can test, and then we can change something and figure out what it did.
All right, so the model itself, what we use for our testing this year is the same model that we've used for a couple of years, Racine Railroad Products. They were kind enough to give us a very large assembly. And The assembly that we start off with, kind of the baseline model, we call it the 2440. It has 2440 unique components. It has just about 10,500 overall components and somewhere around 15,000 bodies. Now, this is going to become important as we talk about other aspects of our testing here. And then we create different variations of this. Like Adrian said, we wanted to test things out. So we have the 2x version of this, same number of unique components, but we doubled up the total number of components, total number of bodies. And then as we kind of scroll through here, we got the 1900. You can see we removed some of the detail here. And as we work through these different models, what we did is we wanted to make sure that we were always working with the same data set, just removing different portions of it, kind of keeping the same modeling methodology. We're working with a universal data set at that point in time. We're not worrying about how things are different. And you can see we strip out things like the cab, or we bring back just the frame assembly at some point in time. Basically bringing this down to some of the smaller level assemblies that people work with on a day-to-day basis, like 35 component assembly. So we tested everything from 20,000 components and all the way down to 34. So,
well, 20,000 components, 34 unique components.
Yeah, exactly.
Which actually comes into play a little bit later in the graphics discussion as well. So, we're going to start with RAM. Now, this is using our new benchmark. We're able to test multiple assemblies, so we're going to show you results from all those assemblies. RAM is critical for everything in SOLIDWORKS. It's kind of like the linchpin for the whole nut. If you don't have enough RAM for the assemblies that you're running, it's going to choke, and it's going to start choking hard, okay? So, it's important to also realize that every assembly has a threshold. That it's the threshold, the RAM that it requires to run, and so you have to at least meet the RAM requirement of your worst, ugliest assembly. And then a little bit more, because you're just going to make it uglier, right? I mean, it's just the way it works. Okay, without enough RAM, the hard drive becomes hypercritical because it's now going to start swapping. Hopefully we're not running into this anymore with the 64-bit environment and all the RAM that we have available to us. Everything runs slower. The OS is now struggling too because it's competing for the same RAM that SOLIDWORKS is, and then everything becomes more unstable. You have more crashing, you have more difficulty in keeping the model even up and running so that you can continue your work at all. We show that to a minor extent in our test results.
So, is there such thing as too much RAM? So, when we ran the benchmark, it was run with 5 different assemblies. We showed you those earlier, 11 different RAM configurations. We didn't bring in any graphics manipulation, so the spins and rotating we left out at this point in time. We ran this on 4 cores at 4.5 gigahertz, and we stuck with our SSD for operation and storage.
All right. It may look a little crowded, the graph, but bear with me and ask questions if you have any, okay? You look at the right over here. Am I blocking your view? Over here? Right there? It goes from the largest assembly down to the smallest assembly that we tested, okay? Correspondingly, the curves, Jesus. Yeah, the curves correspond largest to smallest, top to bottom. Okay, now, a couple of things that we run into is we notice every one of them has a flat. At some point, it kind of flattens out. It won't get faster with more RAM. There's a point where it can't go faster just because you added RAM. So if you've got, say, 16, let's just say you had 20 gig of RAM, anything over that's too much. Too much money-wise. You can never have too much RAM if you're an engineer, really. You like to have a lot of elbow room, but you paid more than you needed to, okay? There is no impact there. Now, what I'd mentioned to a lesser, the instability that you see when you don't have enough RAM, right here. The largest assembly we had could not even run at 4 gig of RAM. It couldn't finish, it wouldn't complete, it kept crashing, dying, we couldn't even get it to happen. That will happen to you if you don't have enough RAM for your assemblies. The swap was on, yes. And we've shown with a couple of even larger assemblies, when you go to swap and you start hitting a hard drive, especially the slower hard drives, for some reason, the slower the hard drive, it makes a big difference. It gets more unstable. I don't know if it has to do with RAM, and I don't know why, but it's a big deal. All right. Now, what we did here is we used this tool called perfmon. Anybody remember the old sys internals? All right, some of you do. Your IT guy remembers. It was part of their religion. All right. Well, sys internals had a lot of great monitoring tools and operating system kind of add-ons for Microsoft. And then Microsoft went and bought them. Bill Gates, he's evil, the whole 9 yards. But he incorporated a lot of this stuff into the operating system. And perfmon is one of the good ones. You can go in there and you can set up little monitors for your processor, for your RAM, for all kinds of stuff I don't understand. All I cared about was RAM. I wanted to monitor how much RAM was being utilized as I ran my benchmark comparing RAM. All right? So, I set it up, told it where to put the files, and it dumps out a file that gives me this graph each time. So I start the perfmon monitor, then I start my benchmark, the benchmark completes, and then I stop the perfmon monitor and look at the results, and it gives me a nice maximum RAM utilization number.
13 gig. Right? Somewhere around 13.
13.3 gig, 3.4 gig. So it tells me that the machine required for both the operating system and SOLIDWORKS, that's important because I didn't run anything but the operating system and SOLIDWORKS when I did these tests. Keep that in mind when you're calculating RAM and stuff. So it tells me what SOLIDWORKS needed, and then I impose that upon my curves running from 16 gig down to 4 gig, and I can see where the inflection, where it starts getting slower, is roughly where I hit the maximum amount of RAM on the machine that I was comparing, or that I was monitoring. It's in that zone somewhere. So you can get a real good ballpark idea if you use these tools. If you use the perfmon tool, just turn it on for, half a day. Sit down and just work with SOLIDWORKS, turn it off, and see what your maximum utilization was. See if you were going over the limit of what you have in hard RAM. It'd be an interesting little experiment for you. All right? But you can see that you can fairly well count on it, going down, 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 and it inflects about where our maximum RAM utilization was. So at this point, I know if I'm doing small, tiny assemblies, less than 100 components, less than 35 unique components, I still need 8 gig of RAM. And I'm hitting the limit of that. So, how many people here do small assemblies, tiny assemblies? Tiny being less than 500 components. All right, that's pretty much everybody. How many of you have less than 8 gig of RAM, though? Just a few. Okay, that's good.
So you're going to want to download this presentation when you get back to work, by the way. Yeah, just so you know.
What was it?
He needs to download the presentation and take it to his boss as soon as he gets back to work.
Oh, yeah, there you go. That'd be good.
All right, so the next thing that we wanted to look at is processor speed. As we talked about before, SOLIDWORKS itself uses no more than 2 cores. The OS can use another 2 cores. And as far as for just running SOLIDWORKS, anything more than 4 cores is overkill at this point in time. We proved that earlier on. So with that as well, you can have more than enough RAM, and you can have more than enough cores. But can your processor be too fast is the question.
Anyone know the answer? Okay.
Exactly. So is there such thing as too much? The benchmark was run with 7 different assemblies, 7 different processor speeds, no graphics manipulation. Once again, we're saving that for a little bit later on. 32 gig of RAM again, and our SSD for operation and storage. So that's kind of where we started with everything.
So this is what we looked at. We utilized the box machine. They've been a great partner for us for many years in doing this. One of the many reasons we like to use them is they do overclock their processors. And when they overclock their processors, they can help me underclock them. So I can use the exact same processor and test just the change in performance based on a speed. I don't have to pull the processor and drop in another one. That's a wonderful way of testing and isolating a variable. So what we did was we tested 7 different assemblies. We went all the way down. This is interesting. All the way down to the very smallest assembly, from 2 gigahertz in half gigahertz increments up to 4.5, and then we tested 4.7 as well. Okay? And we can see 7.5 to 9% performance increase per every half gigahertz we add to our processor. Now the beauty of this is it doesn't matter who you are. It doesn't matter if you're building small or large assemblies. We still saw roughly the same improvement percentage-wise across the board. That's impressive. Now what we also saw was that there didn't seem to be a limit to the improvement. Okay? Now we can't go beyond 4.5, 4.7, so we don't know what's going to happen there, but if the previous curve is any indicator, we're hoping for faster processors, right? It's going to help out a lot. It makes a big difference. So, what I did was I looked at the practical zone. You can't buy 2 gigahertz processor, and if you did, you're going to be suicidal anyway, right? So 3.5, we'll start there. These are the percentage improvements we saw. The largest assembly was 18% faster. The worst we had was 14% improvement going from 3.5 to 4.5 across the board, every sized assembly. So you all knew the answer, but we told you anyway. It's always better to have more processor speed, always. You can't get too much.
All right, so taking a look at graphics. This is
I'm sorry, this would be a good time because we're going to switch into graphics. It's a pretty big shift here. Are there any questions regarding, yes, sir? He's asking what the test protocol was. What did we do with the models? And it's a very good question. What we did is we built an API into SOLIDWORKS that would take the model and drop it into my assembly, my particular assembly. Then we would run operations. We open the model. We save the model. We spin and rotate if we have graphics manipulation turned on. We create features in that model. We create patterns of those features. We build a weldment structure.
Yeah.
We put a logo in there of CATI because we're real proud of ourselves.
And we don't want anybody stealing our program.
Well, there's that too. And we run it through several modeling functions, and then we save the model again. We rebuild it a couple of times throughout the process. We close the model and we measure the time it takes to do each one of those operations. It was a very good question. Now, like we said also, though, before when we had this all built for one model, the one Racine Railroad monstrosity, we did a lot more with it. And the test took like 8 hours on our baseline. It took 30 minutes when we optimized, but it took 8 hours on the baseline. This one is much less intense until we start moving forward with it and we start adding more functionality to the test protocol.
But getting our guy to program more functionality in there for us takes a little bit of planning.
Well, that's because he's a consultant and he goes to billable time first, and I don't have any money to pay him. So,
yeah, there is that too.
So, other questions about, yes, sir? The i7 versus the Xeon processor, it's a very good question. Absolutely, if you're going to do anything with photo rendering, simulation, Anything where you're going to take advantage of multi-core, you're going to have to go Xeon processing, okay? Because that's going to allow you to have 2 processors on the same machine to build up the number of cores that you're going to have. Also, Xeon processors allow you to use error checking RAM. So if that's important to you, you got to go that direction. i7 doesn't allow that. I have not done any comparisons as of Xeon versus i7 for a couple of reasons. One is I'd have to have 2 different machines, and I can't isolate the protocol. I can't figure that out in my head right now. And I don't know how to determine which i7 would be comparable. You know what I mean? So I don't really know how to do a comparison between the 2 chips. That's one of the reasons that all of our tests isolate to a specific chip or a specific brand of video card. We keep it consistent so we're not comparing apples to oranges or something like that. Now, there are other reasons to go with Xeon. Can you think of one?
Go talk to the guys in the blue shirts.
They'll know. They know this.
Basically, one of the main differences between a Xeon processor and a core processor. One is uncore technology. You go Google it, uncore Intel, Xeon, right there. Core that basically talks about flowing that goes around the processor. It's built with bigger data points. It's got bigger data pipes that does better I/O. At the entry-level workstation that you can get from Box or others, you'll see around an E3-based processor, which is Core i7 processor. Principally almost the same exact architecture. There's just some other features and functions that are in the Xeon processor that you won't get with the Core i7. You'll get the PCC memory adder that you're in there. We're using processor graphics for every hand. We're using processor graphics, but I don't see you're going to cover processor graphics instead of it.
No.
But you can talk to Liam up in the booth, that's Shamanic, a couple other guys, Dave Fanjoy, Sam Dollar, over there. That we'll all be up there to answer your questions and help you navigate the differences for us.
They're good guys to work with, just so you know.
Yes, sir.
Did you do anything on your benchmarks for simulations for the different solvers, for which ones will take advantage of the core, which ones won't, which ones need more information?
I did not compare the different processors, mainly because I was getting wildly bizarre answers out of one or the other when I would try different model sets. So I wasn't able to isolate them in the same model set. That just I'm not a sim guy.
And we've tried. It's just been hard to ever kind of pin it down to any one thing. So, and it's kind of like a lot of our testing. It's taken a couple of years, to nail down graphics, for example.
I did some stuff over at Box over the summer, and we were talking about the presentation last year. So we got some sim stuff.
Okay. Perfect. Thank you. You had something?
What do you tell your customers that are reluctant to move from ECC to memory available with i7?
The memory that's available with an i7?
ECC with
i7.
processor. Your customers are reluctant. What do you tell them?
The honest answer, if they're reluctant to move from ECC to i7,
Just your core SolidWorks.
what do I tell my customers who may be unwilling to move off of a Xeon processor with ECC capabilities to an i7?
Yeah, so that's again, you can come visit me in the booth. I don't want to take away from their presentation. A lot of things around
25.
aware of.
Okay.
Google did an
We'll give them
wonderful
20 minutes to go.
Yeah.
Okay, we'll go now.
Talking about propensity of errors, right, and what an error means. Now, there's 4 things that the error means. It's in a part that you're now using really memory where it's a DOS, you're going to get a blue screen. I don't ever get blue screens. I get them once in a while, but not enough to worry about. And the last one is the one that's probably the most important part. It's in your data. And if you get a bit flip in your data and you don't know it, you have a problem. And you don't know it. Okay, about the chocolate and get you food as well. You want to bet.
Xeon, Wes knows his Xeon processor very, very well. Now, you had a question in back. If you could hold that for us, because we want to get into the graphics here before we run out of time. I appreciate everyone's questions. Keep asking them as we go, but now we're going to center on the graphics cards and some of the, what would you call it, oddities with this.
Yeah. So as far as graphics go, we teamed up with NVIDIA this year. Again, they gave us a K620, K2200, and K4200. And what we're looking at is what affects graphics performance. When we look at this list here, these are all the different things that can affect our graphics performance. Everything from the graphics card, driver, CPU, image quality, display style, lightweight mode. All of these different things have an effect on graphics performance. And we'll look at some of the most critical ones that we see for day-to-day use of SOLIDWORKS. So, this is your slide.
Yep. So how do we measure performance of a graphics card? For SOLIDWORKS, we measure it in how fast we can get something done. For a graphics card, it's a little weirder, or maybe less weird. Depends on your perspective. We measure it in frames per second, but we really measure it in the response and the feel of when we put the model into motion. When we hit that middle mouse button and start spinning, what happens? Can you hit the button, please?
Yeah,
do you get a nice, smooth... You don't have a mouse?
Yeah, we're good.
I told you I'd give you my mouse.
There we go.
Do we get a blocking model that spins real smooth? Easy to look at, not as much. Or do we get a very detailed model that snaps and jumps as it goes through its rotation? Or do we get all that detail and the crisp, nice, smooth spin? What are we going to do? So the whole thing is how SOLIDWORKS gets involved with the process of displaying the data. How does it work with the graphics card? And how is that going to impact you on the front end? Oh, I'm holding it. Sorry about that.
No worries. So when we look at graphics, we're looking at how many frames per second the human can perceive. Common thought is 60 frames per second. Some experts, testing has shown at least 220 frames per second. One thing that we have to remember, most of our monitors only go to 60 hertz, 60 frames per second. So monitors that can be found at 120 hertz, even 240 hertz at this point in time. And what your graphics card can do beyond the refresh rate is going to be overkill at that point in time. Now, one of the other things in talking with the NVIDIA guys is VSync for your graphics display, just for SOLIDWORKS, needs to be off for optimal performance.
For SOLIDWORKS and all your really highly visual video games. Big deal there, too. So to turn off the VSync, you got a couple of different options here. But when you bring up, this is NVIDIA, right? So AMD's got their own deal. We didn't test AMD cards. With the NVIDIA control panel into global settings, you can set the vertical sync. It's the last one in the list. You can turn it on, you can turn it off, or you can tell the application itself from the second tab, program settings, to make the decision there, okay? So just get it off one way or the other when you're using SOLIDWORKS. It'll help you out.
All right, so the next thing that we want to look at for graphics is level of detail. Now, on what you're seeing on the screen here, if you notice the object kind of in the bottom that has the lines on the outside of it, you can see as we start to rotate that model, do we get that blocky performance or that blocky look to it? So that's what we're talking about for level of detail inside of SOLIDWORKS.
Now we can set that manually in the system options of SOLIDWORKS. You've got a slider up there that allows you to adjust how much of that you're going to see as you spin the model. How much of it is a relative, it's the best way I can describe it. You move to the left, you get more detail, fewer frames per second, okay? Move to the other side, you get less detail and more frames per second, smoother. You can turn it off entirely and see how you do as well, okay? SOLIDWORKS helps in large assembly mode with this by setting it kind of for you as well. Kind of adds that into their efforts to improve performance in large assembly mode. Okay? But it allows you to get a smoother spin. It doesn't matter what you do. When you take that mouse and you drag it from one side of the screen to the other, your model is going to get there, and it's going to get there quickly. The difference is, was it a smooth, gradual, pretty transition, or did it just go bam? Okay? That's pretty much it. Depends on your needs, right?
So what we saw, graphics as far as large assembly goes, what we're getting here is the percentage of difference is extremely small. When we look at this across all the video cards and our level of detail set anywhere from off all the way up to 100%, all the video cards are kind of performing the same at that point in time. They're all running about, anywhere from as low as 8 or 9 frames per second up to about 21 or 22 frames per second. And the reason for this is, Adrian, I think you got a little bit better explanation than I do as far as the...
What ends up happening is when you get into large assemblies with SolidWorks, the number of components matters and the depth of the assembly matters. How many layers you have, that matters as well. Which really stinks to me because we tell our users to build in the depth you need, especially for a bomb or something like that.
Yeah, for a bill of material.
But also for managing your model, it's much easier. You don't want a flat model, right? But for graphics, it would have been better. Okay? That's unfortunate, right? But when that level of detail, when that depth of the assembly combined with the number of components reaches some threshold that we have not yet identified, SolidWorks slows down, it gets more inefficient in delivering the information to the graphics card as to what to paint. And we see some dramatic results in that. So what ends up happening is regardless of what video card you have, SolidWorks becomes the choke point then, and across the board, they all perform identically. To the point that here at 80% of your level of detail, the 620 was actually the fastest in our test. But if you look at the percentage difference, it's very minor. We're within a margin of error. These are practically the same, okay? So we've eliminated any benefit of the graphics card at that point with the large assembly. So when we look at image quality, what we try to do is find out where we do see a benefit with the better graphics cards, with the more expensive graphics cards, okay? And it's honestly, it's tough to find. But we did. We found it for you. Okay? We'll see if anybody in this room is going to benefit from it, okay? All right. It's when we're working with single parts that have complex geometry and a large amount of tessellation to display the image. So to simulate this, we had to use the image quality settings and just crank it all the way up. We did it in stages to see what occurred, but it took a lot of effort to make this happen. We hit it at 25, 50%, 75, 95, and 100. Now that percentage is measured, zeros over here, 100. Well, to be honest, is a little bit outside the edge here because when we went to the edge, the thing just barfed along. Okay? This increases the fine detail that you can see in a model. It's mostly used for small components, very, very, very tiny components, so that they don't look, so your circles don't look like octagons, that sort of thing. But when you do this, it greatly affects your graphics capabilities. When you get into this area near the red, and you can see as you approach the red, or when you're down here at the low image quality, look at that. The better graphics cards do make a difference. They spin more frames per second, okay? More frames per second than the smaller ones, or the less expensive ones, the less capable ones, whatever. It does make a difference. But this is where Josh's slide earlier that measures frames per second makes a difference and why we brought it up. All of this difference is so far beyond what you are capable of noticing. the worst that we did was 500 and something frames per second. Why do you want to improve on something if you're not going to notice the improvement? Okay? So we keep tracking down. And still, even here at 95%, we're still going at that 220 to 240 range, which is at the edge of your perception. You're talking about spinning models. It's not a big deal. Still no need. Now, when we got all the way up to the top, when we really made this model, I was going to say ugly, but we made it really, really pretty, right? We made it as detailed as possible, as fine as possible. When we did that, now we're talking about only being able to show 30 to 90 frames a second. So you get a 120 hertz monitor, or even a 60 hertz monitor at that point, and start looking in this range, you're going to see a noticeable difference, and that high-end card makes a difference for you. Now, small assemblies, single parts, all of this is where you're going to see this kind of improvement. But does anyone here think that they have a model that requires that level of tessellation to view it comfortably?
Because this kind of goes against everything that I do, which is modeling methodology. And I will tell you time and time again to stay out of the red zone, stay out of that 100% zone.
Yeah. And so if you're going to do what we ask you to do in modeling methodology and stay out of that zone, then you have to build that kind of tessellation into your model naturally. And I can't think of a situation where that would occur.
That's on the graphic regeneration. When you build the feature 3D build, but you still cannot do anything because of the right, it says regenerating graphics.
It's a good question. He asked if we did any testing on the graphics regeneration portion of SolidWorks. We actually stripped that out this year and tested just calculative SolidWorks effort and did the graphics just in the spinning actions.
This was a question of the customers. It is worth investing in a much more expensive video card in order to reduce that time.
No. Yeah, it is not worth the investment for that reason. No, sir. So we found that niche where the expensive graphics card makes a difference. So if you fall in that zone, we got some options for you. Okay? All right.
So,
Oh, I'm sorry, Josh.
yeah, no worries. So what is the large assembly threshold? At some point, SolidWorks determines that an assembly is too big for the graphics card. And this is what Adrian was talking about with the level of detail and the depth of assembly. And we found that across all the video cards, starting off with the 620, the smaller video card. When we had our, you already jumped there? Okay.
I did it for you.
All right, no
I'm
worries.
here for you, man. I'm helping.
Thank you, I appreciate it. You can see we started off with that 570 assembly. We're in the 275, 350 range for frames per second. And this is looking at level of detail from 0 all the way up to 100%, looking at real view in shadows turned on and curvature generation turned on as well. And we can see when we jump up to that 735 level, we're not sure if it's number of components or depth at that point in time. This is some of the next stuff that we're going to start investigating. Our frames per second drop down. You can see we're down into the 20s and 30s at that point in time. When we step up to that 4200 card,
Oh, you did it. Sorry.
yeah, we'll jump you over there. That's, same type of results as we see across there. A little bit higher frames per second, but beyond the scope of what we can comprehend for the most part at that 570 level, and we're still in the mid-30s on that 700 level.
So what may have happened to some of you folks, and I guarantee it's happened to a couple of you. You've been modeling, everything's going great, and then one day you call your VAR, you call the support line, and you say, it worked great 2 days ago, and now it's just dragging. Our thought, our theory, so to speak, is that you crossed the threshold, either with another layer of depth or more components, or you added a big subassembly in there, and it just jumped over the edge.
Yeah, you might have started detailing out your model, putting in all the hardware, and all of a sudden, you were spinning perfectly before you put all the hardware in. As soon as you add all that hardware, now it's just choking and jumping around as you go to spin it. we're thinking you're hitting the threshold at that point in time.
But we can't say that for sure until we test it. So now we got a task for next year.
So now you have a reason to come back next year.
One bit of extra info to add here. You're only looking at the frames per second, but if you start measuring from the interactive time, when you push the button to when you get your model to final position, you'll find that on a high-end graphics card, turning level of detail off will get you there faster than it on because there's overhead in calculating the bounding boxes. So when there's too many components on the screen, it takes longer to calculate the bounding boxes than it does just to let the graphics card handle it and rotate it. Even though the frames per second is low, you're not waiting for that lag to start.
That's very interesting, but I can see we've experienced the lag. When you get a big enough assembly, you can click and you can almost watch it happen as it builds it. As it builds it.
Turn that off, don't wait for the generator. Your frames per second is a little lower while it rotates. Well, so it's, it's slower rotation or it's not quite as smooth on the rotation, but you're not waiting for the bounding boxes to generate and go away when it stops.
All right.
Thank you very much. So, in summary.
3 minutes, Adrian.
3 minutes?
3 minutes.
Oh, God, we're good. 3 minutes. How do you like that? And we're at the second to third to last slide. What's practical for you? And that's what we're looking for. Okay, we're looking for the practical setup that's going to work for you. And we're talking about just using SOLIDWORKS. None of the extra stuff here, right? We're talking about solid-state hard drive. 16 gig of RAM is good for almost everybody. Some people may need more, but it's rare. An NVIDIA K2200 graphics card. That gives you that kind of middle ground between the high end that's not going to buy you anything and the low end that will have holes in its performance for you. There will be places where it lags for you. Okay? A single 4-core processor. You need more cores if you're doing sim and photo rendering, so then you need to start looking at other options to get those extra cores. Processor clock speed, as fast as you can afford, okay? Just make it scream. Local working directory, please use a PDM system. For God's sakes, use a PDM system.
If you're going across the network, PDM.
Exactly. And then optimizing SOLIDWORKS options we'll deal with in Wednesday's presentation, along with a lot of other stuff that's a lot of fun. You'll like that presentation. I guarantee it. Everyone's going to show up, right? Oh, I didn't see enough heads nod there. It's just deadly depressing. It's fun, though. We'll enjoy it. So, we're open for questions. You can get the presentation and many more from that link right there, cati.com. SWW 2015. If you go there and then hit a 4 instead of a 5, you can get last year's presentations. A 3 instead of 4, you can go back another year. We keep them up there forever. This is all the presentations that our team gives at each SOLIDWORKS World. And also, for more information on these topics, you can go to our blog. Now, also, all of these presentations that are available this year at SOLIDWORKS World are put on by the CATI team. Most of the people up here work for me, so I know they're good at what they're doing, so they'll give you good information, okay?
Yeah, and this is number 1 of 4 for me, so please come to all of mine this year. And Adrian's in 3 of them, so.
Yeah, I'm in 3 of them with him, so keep that in mind, and also the link to download the presentations down there. You will be able to get all of those presentations at that link, and we are now open for questions.
Come see me, by the way, if you want me to email you this list. I can email it to you right now.
Yes, sir. The question was, did we account for the amount of RAM that the graphics cards use? And we didn't test that in the least. Nothing about RAM in the graphics cards. Anything else? Anything? Bueller? Anybody remember good movies from the 80s? Yes, sir. Yeah, Wednesday at, what time is it?
Wednesday at 2:45.
Wednesday at 2:45.
We're in the big room on the other side of this escalator.
That's why we're asking you to come. It's going to get pretty, grave.
It'll be sad if you guys aren't there.